In digital imaging systems, color management is the controlled conversion between the color representations of various devices, such as image scanners, digital cameras, monitors, TV screens, film printers, computer printers, offset presses, and corresponding media. The primary goal of color management is to obtain a good match across color devices. For example, the colors of one frame of a video should appear the same on a computer LCD monitor, on a plasma TV screen, and as a printed poster. Color management helps to achieve the same appearance on all of these devices, provided the devices are capable of delivering the needed color intensities. With photography, it is often critical that your prints or online gallery appear how they were intended. Color management cannot guarantee identical color reproduction, as this is rarely possible, but it can at least give you more control over any changes which may occur. Parts of this technology are implemented in the operating system, helper libraries, the application, and devices. A cross-platform view of color management is the use of an ICC-compatible color management system. The International Color Consortium is an industry consortium that has defined an open standard for a color matching module at the OS level. Color profiles for devices, including device-linked profiles that represent a complete color transformation from source device to target device. Working spaces, the color spaces in which color data is meant to be manipulated. There are other approaches to color management besides using ICC profiles. This is partly due to history and partly because of other needs than the ICC standard covers. The film and broadcasting industries make use of some of the same concepts, but they frequently rely on more limited boutique solutions. The film industry, for instance, often uses 3D LUTs to represent a complete color transformation for a specific RGB encoding. At the consumer level, color management currently applies more to still images than video, in which color management is still in its infancy. Overview. Characterize. Every color-managed device requires a personalized table or color profile, which characterizes the color response of the particular device. Standardize. Each color profile describes these colors relative to a standardized set of reference colors. Translate. Color-managed software then uses these standardized profiles to translate color from one device to another. This is usually performed by a color management module. Hardware. Characterization to describe the behavior of various output devices. They must be compared in relation to a standard color space. Often a step called linearization is performed first, to undo the effect of gamma correction that was done to get the most out of limited 8-bit color paths. Instruments used for measuring device colors include colorimeters and spectrophotometers. As an intermediate result, the device gamut is described in the form of scattered measurement data. The transformation of the scattered measurement data into a more regular form, usable by the application, is called profiling. Profiling is a complex process involving mathematics, intense computation, judgment, testing, and iteration. After the profiling is finished, an idealized color description of the device is created. This description is called a profile. Calibration. Calibration is like characterization, except that it can include the adjustment of the device, as opposed to just the measurement of the device. Color management is sometimes sidestepped by calibrating devices to a common standard color space such as sRGB. When such calibration is done well enough, no color translations are needed to get all devices to handle colors consistently. This avoidance of the complexity of color management was one of the goals in the development of sRGB. Color profiles. Embedding image formats themselves may contain embedded color profiles but are not required to do so by the image format. The International Color Consortium standard was created to bring various developers and manufacturers together. The ICC standard permits the exchange of output device characteristics and color spaces in the form of metadata. This allows the embedding of color profiles into images as well as storing them in a database or a profile directory. Working spaces such as sRGB, Adobe RGB, or ProPhoto are color spaces that facilitate good results while editing. For instance, pixels with equal values of RGB should appear neutral. Using a large working space will lead to posterization, while using a small working space will lead to clipping. This trade-off is a consideration for the critical image editor. Color transformation. Color transformation, or color space conversion, is the transformation of the representation of a color from one color space to another. This calculation is required whenever data is exchanged inside a color-managed chain and carried out by a color-matching module. Transforming profiled color information to different output devices is achieved by referencing the profile data into a standard color space. It makes it easier to convert colors from one device to a selected standard color space and from that to the colors of another device, by ensuring that the reference color space covers the many possible colors that humans can see. This concept allows one to exchange colors between many different color output devices. Color transformations can be represented by two profiles or by a device-linked profile. In this process, there are approximations involved which make sure that the image keeps its important color qualities and also gives an opportunity to control on how the colors are being changed. Profile connection space. In the terminology of the International Color Consortium, a translation between two color spaces can go through profile connection space. Color space 1 PCS, color space 2. Conversions into and out of the PCS are each specified by a profile. Gamut mapping. In nearly every translation process, we have to deal with the fact that the color gamut of different devices vary in range, which makes an accurate reproduction impossible. They therefore need some rearrangement near the borders of the gamut. Some colors must be shifted to the inside of the gamut, as they otherwise cannot be represented on the output device and would simply be clipped. This so-called gamut mismatch occurs, for example, when we translate from the RGB color space with a wider gamut into the CMYK color space with a narrower gamut range. In this example, the dark, highly saturated purplish-blue color of a typical computer monitor's blue primary is impossible to print on paper with a typical CMYK printer. The nearest approximation within the printer's gamut will be much less saturated. Conversely, an inkjet printer's cyan primary of saturated mid-brightness greenish-blue is outside the gamut of a typical computer monitor. The color management system can utilize various methods to achieve desired results and give experienced users control of the gamut mapping behavior. Rendering intent. When the gamut of source color space exceeds that of the destination, saturated colors are liable to become clipped, or more formally burned. The color management module can deal with this problem in several ways. The ICC specification includes 4 different rendering intents: absolute colorimetric, relative colorimetric, perceptual, and saturation. Absolute colorimetric, absolute colorimetry, and relative colorimetry actually use the same table but differ in the adjustment for the white point. Media. If the output device has a much larger gamut than the source profile, All the colors in the source can be represented in the output. Using the absolute colorimetry, rendering intent would ideally give an exact output of the specified CIELAB values. Perceptually, the colors may appear incorrect, but instrument measurements of the resulting output would match the source. Colors outside of the proof print system's possible color are mapped to the boundary of the color gamut. Absolute colorimetry is useful to get an exact specified color, or to quantify the accuracy of mapping methods. Relative colorimetric. The goal in relative colorimetry is to be truthful to the specified color, with only a correction for the media. Relative colorimetry is useful in proofing applications, since you are using it to get an idea of how a print on one device will appear on a different device. Media differences are the only thing you really would like to adjust for. Obviously there has to be some gamut mapping going on also. Usually this is done in a way where hue and lightness are maintained at the cost of reduced saturation. Relative colorimetric is the default rendering intent on most systems. Perceptual and saturation. The perceptual and saturation intents are where the results really depend upon the profile maker. This is even how some of the competitors in this market differentiate themselves. These intents should be created by the profile maker so that pleasing images occur with the perceptual intent, while eye-catching business graphics occur with the saturation intent. This is achieved through the use of different perceptual remaps of the data as well as different gamut mapping methods. Perceptual rendering is recommended for color separation. In practice, photographers almost always use relative or perceptual intent, as for natural images, absolute causes color cast, while saturation produces unnatural colors. Relative intent handles out of gamut by clipping these colors to the edge of the gamut, leaving in gamut colors unchanged, while perceptual intent smoothly moves out of gamut colors into gamut, preserving gradations, but distorts in gamut colors in the process. If an entire image is in gamut, relative is perfect, but when there are out of gamut colors, which is more preferable depends on a case-by-case basis. Saturation intent is most useful in charts and diagrams, where there is a discrete palette of colors that the designer wants saturated to make them intense, but where specific hue is less important. Before the actual rendering intent is carried out, you can temporarily simulate the rendering by soft proofing. It is a useful tool as it predicts the outcome of the colors and is available as an application in many color management systems. Implementation. Color Management Module. Color Matching Module is a software algorithm that adjusts the numerical values that get sent to or received from different devices so that the perceived color they produce remains consistent. The key issue here is how to deal with a color that cannot be reproduced on a certain device in order to show it through a different device as if it were visually the same color. Just as when the reproducible color ranged between color transparencies and printed matters are different. There is no common method for this process, and the performance depends on the capability of each color matching method. Some well-known CMMs are ColorSync, Adobe CMM, Little CMs, and Argyle CMS. Operating system level. Apple's Mac operating systems have provided OS-level color management APIs since 1993, through ColorSync. Mac OS X has added automatic color management automatically in the OS, and applications have to work around this to provide more accurate color management. Since 1997, color management in Windows is available through an ICC color management system. Beginning with Windows Vista, Microsoft introduced a new color architecture known as Windows Color System. WCS supplements the image color management system in Windows 2000 and Windows XP, originally written by Heidelberg. Operating systems that use the X window system for graphics can use ICC profiles and support for color management on Linux. Still less mature than on other platforms is coordinated through OpenImage at FreeDesktop. Organ makes use of little CMs. File level. Certain image file types include the notion of color channels for specifying the color mode of the file. The most commonly used channels are RGB and CMYK. An additional alpha channel may specify a transparency mask value. Some image software perform automatic color separation to maintain color information in CMYK mode using a specified ICC profile such as US Web. Coated V2. Application level. As of 2005, most web browsers ignored color profiles. Notable exceptions were Safari, starting with version 2.0, and Firefox starting with version 3. Although disabled by default in Firefox 3.0, ICC v2 and ICC v4 color management could be enabled by using an add-on or setting a configuration option. As of 2012, notable browser support for color management is Firefox, from version 3.5 enabled by default for ICC v2 tagged images. Version 8.0 has ICC v4 profiles support, but it needs to be activated manually. Internet Explorer. Version 9 is the first Microsoft browser to partly support ICC profiles, but it does not render images correctly according to the Windows ICC settings and therefore provides no real color management at all. Google Chrome uses the system-provided ICC v2 and v4 support on OS X, and from version 22 supports ICC v2 profiles by default on other platforms. Safari has support starting with version 2.0. Opera has support since 12.10 for ICC v4.